Welcome to This Explainer. Today we're going to tackle a concept that honestly sounds like something straight out of a top-secret sci-fi lab. But don't worry, we are completely demystifying the world of reverse engineering using some incredibly simple, everyday analogies. If you've ever wondered how modern engineers manage to recreate, fix, or even improve complex parts without having any of the original blueprints, well, you are in exactly the right place. So grab your notepad and let's dive right in. Okay. Picture this for a second. You've got this beautiful vintage espresso machine, or maybe a classic car you've been restoring, or even just a super specific piece of manufacturing gear at your job. Suddenly, a crucial little gear snaps in half. You call the manufacturer and they tell you, oh, sorry, we stopped making that specific part 20 years ago. What do? Just throw the whole machine in the trash? No way. That deeply frustrating real-world scenario is exactly the problem that reverse engineering brilliantly solves. It's basically the ultimate tool for bringing obsolete things back from the dead. To really wrap our heads around this, I want you to think of what I call the reverse chef analogy. See, traditional engineering is kind of like being a baker with a brand new recipe. You have a great idea, you write down your list of ingredients, you mix them all up, and boom, you bake a cake. You go straight from a concept to a physical object. But reverse engineering? That's entirely flipped. It's like taking a bite of an incredible, already baked cake and then working backwards to figure out its exact secret recipe so you can bake it yourself. You start with a final physical product and literally deconstruct it to find the core idea. To make sure we really master this reverse chef mindset, here's our roadmap for today. We'll start with what reverse engineering is, then hit the 4-step workflow, look at how 3D scanners work, see how we go from digital back to physical, and finish up with the strategic benefits. All right, section 1. What is reverse engineering? Let's pin down the concept. Let's look at how these two engineering worlds actually contrast. Follow that top path for a second. That's the traditional flow. It starts with the light bulb, the idea. Then it moved into CAD, which is computer-aided design software, and it finishes with a shiny new physical gear. Now look at the bottom path. Here, our engineer starts with a broken, rusted gear. But using a 3D scanner, they translate that physical, broken part into a pristine digital model inside their CAD software. They're essentially writing down that discovered recipe. And from there, they can digitally fix any flaws and manufacture a perfected, modified product. Moving right along to section 2, the workflow. Let's look at the 4 steps it takes to pull this off. Conceptually, this whole journey boils down to 4 main phases: data acquisition, mesh generation, CAD reconstruction, and finally manufacturing. Let's break down exactly what happens in each one of these. In step 1, data acquisition, we use a 3D scanner. Think of this as taking millions of tiny measurements of our cake to figure out its exact shape. That creates what's called a point cloud. Step 2 is mesh generation. This is where those scattered dots are connected mathematically to form a surface. Honestly, it's just like connecting the dots in a giant 3D puzzle. Step 3, CAD reconstruction, is where the heavy lifting happens. The mesh is refined and converted into a solid, editable digital blueprint. And lastly, step 4 is manufacturing, where we use tools like 3D printers to turn that perfect digital file back into a physical reality. Which brings us to section 3. How do scanners actually work? Let's look at the hardware making this possible. Imagine you have a really complex physical part, like a metal engine manifold, and you're scanning it with a specialized camera system. That scanner is actively reading the surface data of the object. As it sweeps over all those curves and sharp edges, it's plotting the physical dimensions onto a computer screen in real time. This generates our point cloud. It is literally capturing reality and instantly digitizing it. Now, if you're new to this, let's quickly anchor this term. What exactly is a point cloud? Well, it's just a massive collection of XYZ coordinates floating in digital space. Picture yourself taking a microscopic ruler, measuring millions of tiny individual spots on the outside of an object, and placing a little digital dot at every single spot. When you zoom out, all those millions of individual dots form the ghost-like shape of your object. So how do we actually get all those dots? We've got 3 main tricks up our sleeve. First is structured light. This projects a grid pattern onto the object and measures how those lines bend over the curves. It gives you incredible high-resolution detail. Second, we have laser scanners. These shoot out laser beams and measure the exact time it takes for the light to bounce back. It's incredibly precise and great for large-scale industrial stuff. And third is photogrammetry. This uses multiple overlapping 2D photographs taken from different angles to stitch together a 3D model. It is a highly accessible and really cost-effective way to scan. You might be wondering, why go through all this trouble? Why not just use a trusty measuring tape or some calipers? Well, the advantages of scanning are absolutely massive. First off, high accuracy. You get exact dimensions every single time. It's also super fast. You can digitize complex parts in literally minutes. But honestly, the biggest win is non-contact measurement. If you're reverse engineering an ancient, fragile vase or a super delicate artifact, you can map it perfectly without ever laying a finger on it. Plus, it easily handles weird, organic shapes that would be flat out impossible to measure by hand. Okay, section 4, from digital to physical. We've got our recipe, so it's time to finally bake that cake. The progression for additive manufacturing, which is just a fancy term for 3D printing, starts with our perfected CAD model. That model gets converted into an STL file, which essentially translates the smooth curves of your design into a mesh of tiny triangles that the computer can easily digest. Then comes a totally crucial step, slicing software. Think of slicing just like planning out a massive, multi-tiered wedding cake. The software literally slices your digital model into hundreds of incredibly thin horizontal 2D layers. It's basically writing out the step-by-step instructions for the printer to build the object from the ground up. To keep our simple analogies rolling, picture an FDM 3D printer as a highly advanced robotic hot glue gun. Up at the top, you have the extruder, which feeds a spool of plastic wire right into the hot end. The hot end does exactly what it sounds like. It gets hot and melts the plastic. Then the nozzle precisely squirts that molten material onto the print bed, layer by microscopic layer. All the while, these little stepper motors are controlling the exact movements left, right, up, and down, totally coordinated by the main controller board. It is an absolute symphony of mechanics, all driven by our reverse engineered data. Finally, section 5, strategic benefits. Let's zoom out and look at why this is such a game changer. The strategic impact here is just huge. First, rapid product development. You dramatically speed up the time it takes to go from a broken part to a working prototype. Second, cost reduction. Back in the day, manufacturing meant paying for incredibly expensive custom metal molds. With reverse engineering and 3D printing, you skip that entirely. Third is accurate reproduction, allowing you to flawlessly recreate incredibly complex stuff. And finally, continuous improvement. This one is my favorite. You aren't just copying an old part, you're turning a static physical object into a digital asset. You can thicken weak points, shave off unnecessary weight, and print a final part that is actually way better than the original ever was. Real quick, let's recap the tools and terms of our kitchen that we use today. Point cloud is our raw dotted coordinate data. Mesh is the connected surface. CAD is the software where we tweak the recipe. STL is the file format we send to the printer. Slicing is chopping the model into printable layers. Additive manufacturing is building it up layer by layer. The extruder and hot end melt our plastic, and photogrammetry is making 3D models using just regular 2D photos. If you've got a handle on these terms, you essentially speak the language of modern reverse engineering. And that brings us to the end of today's explainer. We've taken a broken physical object, extracted its digital recipe, and brought it back to life, better than ever. So I want to leave you with a question. Try applying this reverse chef mindset to your own world. If you had a 3D scanner, CAD software, and a 3D printer sitting right on your desk today, what broken, forgotten, or completely unreplaceable object in your home would you bring back to life? Think about it. Keep learning, keep fixing, and I'll catch you in the next explainer.